Hello friends, welcome back to yet another video. So in this video, I am going to discuss something about linear regression. What we can do in this session is I'll just give you a brief intro about linear regression, and then majorly we'll focus on what are the assumptions that we make while building a linear regression model. This particular topic is very important because this is also one of the important topics on which you will definitely be asked a question if you attend any ML interview. So let's try to understand it. Let me first talk about the linear regression model. When we look at a model, a linear regression model, so the model actually looks like this. Y is equal to, which is a target variable, beta naught plus beta 1 and then x, and then there is a random error or a random noise, so eta. So where eta is a noise term or an error term which has a distribution with the variance sigma square and mean 0, and it has a normal distribution. So this is an assumption, or this is a model how it looks like. When we look at this model, so we naturally get a question. Always in our high school, whenever we see linear regression, we always see y is equal to mx plus c, or y is equal to beta naught plus beta 1x. We'll stop here. There is no error term that is included. So then all of a sudden when we come to ML world, we see a particular term called error term, and that becomes the most significant of all this equation. So what is the difference? Why do we all of a sudden look at a different model? So what we see in our high school mathematics or high school class is it's only a fixed or a deterministic linear regression model. So y is equal to beta naught plus beta 1x. So where y is a fixed variable and x is also fixed. So these values are actually fixed. They are not random. Whereas now what we are looking at is a probabilistic linear regression model. So very important. So where is that probability coming into picture? So that is coming into picture because of eta term, which has a probability distribution of normal distribution, and then because of that it will become a probabilistic model. So that is one of the major differences that we will have to understand. So let's look at individual terms and try to understand it. What is y is the target variable, and then it is a random variable. So that is the most important thing. Earlier in a deterministic model, y is not a random variable, y is a fixed variable, but now y is a random variable. What about x is the predictor variable, and coefficients which are beta 1 and beta naught, all of them are fixed. They are not random. So that means their values don't change, rather their values are fixed. The quantity epsilon is the error term, which is a random variable again. So assumed to be normally distributed, as we had discussed, with an mean of 0 and a variance of sigma square. This error term is the most important term. What is this error term consists of? The error term actually consists of probably a variable that is missed, or it consists of an error in the data collection. It consists of inherent noise in the process. Let me just explain something more about this particular error term, because that becomes a very crucial one for our understanding, especially the assumptions one. So what does it mean? So if I take a concrete example of a linear regression, let's take our popular data set, Boston data set, and then in that data set, if we look at the target variable, that the target variable is the value of the house, whereas my x will be some features. Let's say what is the area of the house, how many rooms are there, which locality it is. So all that consists of x. So I have to taking those values, so I have to predict the value of the house. For example, let's say I have considered only one variable. Let's say I have considered what is the area of the house. So if I define my model in terms of only area of the house, okay, and then how much value it will cost. For example, if I take area of the house is 15 units, so that units can be anything, but let's assume that the area of the house is 15 units. If it is 15 units, let's say my house may cost let's say around 48 or 49 dollars, let's say those many dollars. But every time my house has 15 units of area, it may or may not cost 48 dollars. It can cost more than 48, it can cost less than 48. That depends upon a locality. For example, if the locality is a costly locality, a house which has the same area may cost more, whereas the same house located in a lesser locality would cost less. So that means my house has another variable locality, but in my while modeling it, I have not considered it. So I have ignored it. So where should I capture that? I will capture that in the error term. That means I am actually a variable which needs to be included in the model. I have not included it. Why I have not included it? Probably I don't have an understanding about the process. This model is very simple and we know it, and that's why we are talking about the locality. But some processes or some models about the data, we don't even know which factors would influence the target variable. In those cases, obviously, we may miss it. So that needs to be captured somewhere. So that is captured in this error term. Sometimes even in the data collection there may be errors creeping in. For example, when we are calculating the house value, so wherever however we calculate this house value, probably we may do it by survey or we may do it by something else. Whenever we are doing it, the data may not be collected properly, so there may be errors. Not only this, there are places where we collect the data through the instruments will also give some errors, like in the sense that the precision may not be very high. Instead of reading 2.5 as one of the reading, 2.52 as one of the reading, probably because of the precision of the equipment we may read that as 2.5. So there is an error of 0.02. So where does that 0.02 be gathered? So it will come into error term. Sometimes the process itself is inherently noise. So there will be a noise in the process itself. Not all the processes are deterministic. Some processes are random. So that could also be the case where my y will change. So to capture all those things which are not included, so that is why it is called as catch-all terms. It could be a variable that is missed out, or it could be error in the data collection process, or it could be the inherent noise in the data, inherent noise in the process which is generating this data. All of them will be included in this error term. So what is the nature of the error term? So there is an assumption that we are making about this error term, which we will discuss in the next slide. So that becomes the most important one. So in general, this is all about the model, how we describe this model. So then what are the assumptions that we are making while modeling this data? So let's say I am given all these data points which are shown in the circles, and then I need to fit a straight line or a linear regression. Since it's a linear regression, I need to fit a straight line. So this straight line will be the best fit line given this data. So how can I find out this best fit line? So to fit this line, so what are the assumptions that I am making to fit this best line? So that's the important question. So this is an important interview question, so we need to understand very clearly. First assumption that we are making is we are saying that okay, the relationship between x and y is a linear one. So that's an assumption that we are making. It may be linear or may not be linear, but when we are fitting a linear regression model, what we are assuming is the relationship is linear. So that is why we are fitting a linear model. So that's the first assumption that we are making. The second assumption that we are making is the normality assumption. What does this normality assumption say? It says the distribution of the error terms is normal. You remember that we have said that a linear regression model will always have this error term. So that error term, the assumption of the error term is that error term has a probability distribution. That probability distribution can be anything, because there are many continuous probability distributions. For example, there is a normal distribution, t distribution, or there are multiple distributions that are available. But there is an assumption that we are making. The assumption is that this error term has a normal distribution. When we say normal distribution, it is parameterized by two quantities. What are those two quantities? One is a mean value, the other one is a variance value. So we are assuming that this error term will always have a normal distribution. So it also can be interpreted in a different way or using a different one. What does it say? The distribution of the error terms is normal, or when I say the distribution of the error terms is normal, we are also equally saying the y, or the conditional expectation, or the conditional distribution of y at a given x is also normal. What does that mean? This is an important point to understand. What does that mean? For example, let's say if I consider one data point, or let's say if I consider an x of this, okay, let's say 23 or 22 value, okay, when at x is equal to 22, so that when my area of the room or the house is 22, what could be my value of y be? It is only just 52 or 55. It ranges from around $100 to, it can even go up to around $20-30. So that's the distribution that I have. Where is this distribution coming from? This distribution is coming from, the distribution in the y is coming from the distribution in the error. So if error is normally distributed, then the y is also normally distributed. So that's another way of stating it. So the normality condition, what does it say? It says that the error terms are normally distributed, or the conditional expectation of y at a given x. It is a very important. It's a conditional distribution, not the normal distribution. I will tell you what that difference is. What it says is the conditional distribution of y is normal. That means for a given x, the y is normal, but not the distribution of the target is normal. I am not saying that all these y, so these are all my targets. This is one target, second target, third target. So these are all circles of target. I am not saying the distribution of all these circles is normal. I am saying for a given x, my y is normally distributed. For a given x, my y is normally distributed. For a given x, my y is normally distributed. I am not saying that all these y's are normally distributed. So that is a wrong way of saying it. So it is not the distribution of the target is normal, but the conditional distribution of the y is normal. So that's a normality condition. Then the other one is homoscedasticity. What is homoscedasticity mean? It means homo means same, skedasticity means variance. So what does it say? It says that the variance of the error term is again same across observations. What it says, we have said my error term has a mean value of 0 and then it has a variance that is sigma square. Okay, that also means when I say that variance of the error term is same, it also means variance of conditional distribution of y, that this distribution is also same, because whatever since epsilon is a random variable with a normal distribution, so y also has to be a random variable with normal distribution with mean 0 and sigma square as its variance, because there is no other random term, so everything else is a fixed. So that is why y totally follows the pattern which epsilon follows. So that is what it says. What it says is variance of the error term, that is epsilon, is same across the observations. That means, for example, if I consider my distribution of error terms here, I said the variance could be, let's say, 2 units here. Then here, can it be 3 units? No, it cannot be 3 units. The variance here also has to be 2 units. That is an assumption that we are making. That means this distribution, the normal distribution at every x will have same mean, that is 0 mean, and it will also have a distribution of same variance. So that is what the homoscedasticity assumption mean. So then the last one that we are going to see is the last assumption is independence. What does that say? It says that errors are uncorrelated in observation. So for example, if I take any of the observations, or it also says that the error terms are uncorrelated. So all these errors, when we see all these error terms, okay, these errors are uncorrelated. That means they are, one error does not have any bearing on the second error. That means they don't have any dependency. They are completely independent. So the data is not a dependent data, rather it's an independent data. So that is why we are able to actually deal this with a linear regression. So these are four important assumptions that we are making while building a model. Most of the times, one interesting question that comes to my mind is always, when did I assume? I had built my linear regression models n number of times. Where did I assume? When did I assume while building it? I have just kind of went into sklearn and then I said that dot fit and then done. I got it. But where did I assume? So this is an important one to understand. Where did we assume all these assumptions? So what we have done actually is, while building a linear regression model, all that we are doing is, it's not just we are building this line for a given data, we are also doing something else. What are we doing? We are doing some more analysis on that. So that analysis is where we are actually assuming. What is the analysis that we do on a linear regression model? What we do is we estimate the parameters. What are the parameters? So in the linear regression model, all that I estimate is what is my beta naught and what is my beta 1. So these are the two parameters that I estimate from this data. So when I estimate when I estimate those parameters, I will say, okay, my beta naught is 10 and beta 1 is 20. So my linear regression model is y is equal to 10 plus 20x. So that is what I say. When I say that, what I am saying is, I am also at the same time calculate, is my parameters are they statistically significant? Of course I have calculated it, but are they significant? Is my slope value 20, is that correct, or is that statistically significant, or it's just a kind of probably issue with the sample that we have collected and the model that we have built on? It could be a sample issue. So to uh, get that statistical significance, we need to do some statistical significant tests. That means we calculate a p-value for that parameter, beta naught and beta 1. Then we will say if the p-value is significant, then we will say, okay, my parameters are statistically significant. They are not a fluke. They are not a, there is some, not a bias or something in the sample which has caused it to be 10 or 20, but rather it is a real population parameter. So that is what it says. If you don't understand what is the difference between sample and then population, how it is relevant in building machine learning models, you just watch my another video which I have made on the sample and then population and the machine learning models. Then we will also have to we will also calculate what is my standard error, what is the confidence interval of my prediction. For example, if I predict my target variable for a given x is going to be 100 units, so is my value going to be only 100, or it will have an upper bound and lower bound? Of course it will have an upper bound and lower bound. Why? Because it is not a deterministic process. It is a random target is a random one. So since it's a random, so it will always have an upper bound and a lower bound. So how do I calculate that? By having a confidence interval. Where do I get the confidence interval and standard error? I get all these things by calculating, by having a distribution of y, or I will assume a distribution of y. What is the distribution that I am assuming? So I calculate standard error, I calculate confidence intervals, I calculate significance of the parameters. All these things I calculate based on the distribution of y, or rather the distribution of the error terms. If I assume a distribution of normality, then all these values will have one meaning. If I don't assume that, then all these parameters will have a different meaning. So the analysis that we do on the parameters, on the confidence intervals that we give, all of them depend upon the type of distribution that error term follows, or rather the conditional expectation y given x follows. So in one sense, what we will do is, for example, if any of those assumptions, fail, what will happen is, what we are going to do is, we are saying whatever the interpretation that we give to our model, of course we will have to give some interpretation to the model. That is why we are building it. So whatever the interpretation that we give about its coefficients, or about the target value that we predict, or about the statistical significance of these parameters or coefficients, all of them are going to be wrong if these assumptions are not correct. So that means we will actually probably keep a more confidence in the model where we shouldn't have actually done it. So every interpretation of the model actually falls apart. So that is what would happen. So what we need to do in those such situations, so what we need to do is, we need to use a different model. For example, if we think that the linearity is not a correct relationship, what we need to do is, we should not use linear model. We probably have to use non-linear models, or we have to use some other models. When there is no homoscedasticity, or rather it has heteroscedasticity, then if the normality condition is not met, and if the data is not independent, then if it is data or errors are correlated, then we should not actually use this. Rather we should use some time series model, because there is a correlation between one data point and the other data point. So all these things are significantly important when we are building this model and interpreting the model. So that is why this particular piece of information becomes very, very important. So hope this brings me to the end of this video. Hope you may have enjoyed it, and then have a good day. Bye.